So the first thing I want to do is talk about, before we look at planes in 3 dimensions, I want to make some correlations in 2 dimensions. And so let's draw our 2-dimensional plane, our XY plane, but in the same orientation as it is in the 3 dimensions. So this is our positive X and this is our positive Y. And let's just analyze the equation X equals 2, for example. Lots of people make big mistakes when they think of X equals 2. This equation tells us about X. It tells us nothing about Y. So Y has no restrictions in this equation. Okay? So if I were to graph this equation X equals 2, I'd want every single point in this 2-dimensional plane where X is 2. Well, X is positive 2 here. For example, here's a point where X is 2. But also, this point over here, X is 2. Y just happens to be a different number. Y is positive there. And in fact, you can see that when you go to graph this, X equals 2, you simply get this line that goes through the x-axis at 2. Okay? And if I wanted to graph Y equals negative 4, I would locate negative 4, 1, 2, 3, 4, and imagine every point where Y is negative 4. So that would be any point on this line. Okay? And so what I want to do now is take these same 2 equations and look at them in 3 dimensions, okay? So I'm going to move some things around so we have some space down here to draw the 3-dimensional version and see what happens. In fact, let me change this X line. Let me make it red so it stands out a bit more. Okay, so now we do the same thing. If I want to graph X equals 2 in 3 dimensions, there are no restrictions on Y or Z. So X equals 2 is right here. So when I'm just looking at the 2-dimensional XY plane, I have this line, right? All of these points are where X equals 2 in the 2-dimensional plane. But then I've got to think about, what about those Z values? They could be anything as well, right? So for example, this point up here could be where X equals 2, as long as it's in this same, right above this line, X equals 2. And so all these points here, as long as they're right above this red line or right below this red line, they also have an X value of 2. So what ends up happening is you get a plane. And so it's kind of hard to draw. It goes forever right and left, but it's this surface, right? This vertical wall sitting at X equals 2. This wall never touches the y-axis, for example. It never touches the z-axis. It's this pane of glass sitting here at 2, this red pane of glass. Okay? And so this now, instead of being simply a line, expanded, this, you could imagine it's a bunch of lines stacked on top of one another. Right? Everywhere above and below where X equals 2. So the same thing is true for Y equals negative 4. So negative 1, 2, 3, 4. And the 2-dimensional space looks like this. But now you've got to consider that 3rd dimension, the vertical dimension. So you've got all these lines now for all those values of Z as well. So you get a plane over here. So this is a pane of glass. This is a plane that runs front to back through Y equals negative 4. And I apologize if it's hard to see with both of them, but I hope you get the point. You can stack these lines in the 3rd dimension to get a plane. If you expand this dimension system to 3 dimensions. And so when you have a variable equals a number, you just simply get a plane and it goes through that axis at that number. So the X equals 2 plane goes through the x-axis at 2. So can you tell me what the XY plane would be called? It's a plane. Okay, we could write an equation for the XY plane. So let me get rid of a lot of this. So now we're talking about this 2-dimensional plane here, right at the surface. So we're talking about this plane down here. Well, that would be where Z equals 0, right? Because this plane has no vertical change. It's z is 0 everywhere in this plane. Okay, so of course we're not looking at any sort of unusual planes that might be tilted or something. We're looking at um, completely flat planes horizontally, vertically, front to back. Okay, and that's what the focus of this video is. That's why it's called simple planes, and that's not very descriptive, but that's a simple, appropriate title that I could come up with.